In 1926, theoretical physics reached a pivotal turning point when Erwin Schrödinger introduced wave mechanics, fundamentally transforming our understanding of the subatomic realm. At the heart of this milestone is his iconic time-dependent wave equation, which provides the mathematical framework for how quantum states evolve over time. By modeling physical systems through continuous wave functions, Schrödinger established a vital cornerstone of modern quantum theory. By the early 1920s, physics faced a major crisis as the Bohr-Sommerfeld model began to break down. While it accurately described simple hydrogen spectra, it failed for complex atoms like helium. The core issue lay in quantum jumps. To absorb or emit radiation, electrons supposedly teleported between fixed orbits without traversing the space in between. Defying classical mechanics, this ad hoc explanation deeply frustrated physicists, signaling an urgent need for a new framework. A sharp rivalry emerged between two competing visions of quantum theory. In 1925, Werner Heisenberg proposed matrix mechanics, an abstract framework using infinite-dimensional matrices focused purely on observable spectral transitions. Though powerful, it was difficult to calculate and physically unintuitive. By contrast, Erwin Schrödinger's 1926 wave mechanics offered a far more accessible approach. Utilizing linear partial differential equations to model continuous matter waves, Schrödinger enabled physicists to apply familiar principles from classical acoustics and wave optics to the subatomic world, offering a welcome, intuitive alternative to Heisenberg's non-spatial mathematics. During Christmas 1925 at Villa Frisia in Arosa, Switzerland, Erwin Schrödinger synthesized three fundamental concepts: Louis de Broglie's matter waves, Albert Einstein's gas degeneration theory, and William Rowan Hamilton's optical mechanical analogy. Though his initial relativistic formulation, later known as the Klein-Gordon equation, failed to account for hydrogen's fine structure due to the unknown nature of electron spin, Schrödinger quickly pivoted to a non-relativistic approach, ultimately yielding his famous wave equation breakthrough.
Here, we dissect the anatomy of a quantum masterpiece, Schrödinger's wave equation. At its core is the wave function, psi, which completely describes the quantum system's state, a concept later interpreted by Max Born as a landscape of probability density. The time evolution component dictates precisely how this wave function transforms and propagates across time. Balancing it is the Hamiltonian operator, h, capturing the system's total energy through its combined kinetic and potential forces. Together, these fundamental components form the mathematical engine governing the dynamic subatomic world.
The true magic of Schrödinger's equation lies in the imaginary unit, I. Without I, the equation describes simple heat conduction, where waves inevitably flatten, dissipate, and disappear. Introducing I fundamentally alters the geometry of reality, transforming a decaying curve into a perpetual, non-dissipative quantum probability wave. As physicist Freeman Dyson remarked, the square root of -1 is one of nature's most profound quirks, serving as the essential mathematical key that sustains quantum states and enables probabilities to endure across time. Quantization is not an arbitrary, magical rule, but a natural mathematical consequence of boundary conditions. Just as a guitar string pinned at both ends vibrates only at specific natural harmonic frequencies, an electron wave confined within an atomic potential well can only exist in discrete standing wave patterns. An atom's discrete energy levels are simply its natural acoustic resonances, its eigenvalues. By treating quantization as an eigenvalue problem, wave mechanics elegantly demonstrates how discrete quantum states emerge naturally from the physics of wave confinement. In his landmark 1926 paper, Quantisierung als Eigenwertproblem, Erwin Schrödinger delivered the ultimate proof of wave mechanics by applying his equation to an electron in a central Coulomb potential. The calculation perfectly reproduced the hydrogen atom's energy levels and spectral lines, proving that atomic structure emerges directly from the mathematics of continuous standing waves. Schrödinger's work rendered Bohr's ad hoc quantum jumps obsolete and grounded atomic theory in continuous physics. Despite their initial rivalry, Erwin Schrödinger dismantled the divide later in 1926 by proving that wave mechanics and Heisenberg's matrix mechanics are mathematically identical. Whether describing the subatomic realm through Heisenberg's discrete algebraic states or Schrödinger's continuous spatial fields, both frameworks express the exact same physical reality. Ultimately, they are simply two distinct mathematical languages revealing one unified truth. Schrödinger's 1926 breakthrough did far more than solve an isolated atomic puzzle. It delivered a definitive operating manual for the microscopic universe. By equipping humanity with the visual and mathematical vocabulary to interpret matter waves, the Schrödinger equation became the essential foundation for modern chemistry, solid-state physics, and quantum technology. Serving as a true blueprint of modernity, this single mathematical triumph continues to power and shape our technological world.